Thanks a lot for inviting me, and thanks everyone for making it today. So today we have divided our talk into radio and X-rays, and I'll try to motivate why do we need these wavelengths. I will be covering broader cosmology, which is my primary field of interest, and what makes us design these kinds of very weird looking systems that you are looking here. So with that, I'll get started. And yeah, please feel free to ask questions anytime. Of course, we'll be open to questions at the end too. So the very first thing where I think astronomy differs very significantly from major disciplines is the length scales involved in our problems. And it's a sheer range from kilometers to megaparsecs. And our brains are mostly incomprehensible to basically imagine these kinds of scales. And so in this talk, I will mostly be talking about what we call as the large scale structure. So for the public here, I'll just want to motivate it with this slide. And these are the kind of objects that we are familiar with. We have a human right there to just set the scales right. And we can basically now move the scroll and see what kind of length scales we keep on uncovering as we move towards the right of the spectrum. Right. So this is basically the kind of minimum. We're talking about 10 raised to 3 to 10 raised to 4, so roughly a kilometer. And we start uncovering these asteroids and some of the planetary satellites, and then we can move further. We can go to some thousands of kilometers, and suddenly we start seeing our more familiar solar system objects like Earth and some of the stars. But this does not end here, especially for cosmology that I'll be talking about. So we'll move further. And we are already now talking to scales which are slightly incomprehensible. We're talking about 10 raised to 10 meters, which is basically a meter followed by 10 zeros. And here we are still looking at few compact objects, something that maybe our colleagues will discuss later. And I'll fast forward this to then get to the relevant scales that we are interested in, which is parsecs and light years. And just a definition is, it's the amount of time light takes to travel. Light year basically is the distance it travels in 1 year, and parsecs is roughly 3 times that. So that is the kind of length scales where cosmology gets to be very interesting. Because in cosmology, what we are looking at is large scale structure of the universe, and I'll get on to that later. But we'll keep moving. This is yet not the end. So we'll continue. And now we are not looking at specific stars, but we are starting to look at cluster of stars or even galaxies, like we live in Milky Way galaxy. So we are already at that kind of a length scales. So it's not 1 light year, so which is basically light does not take 1 year, but it can take tens of thousands of years to travel across these galaxies. And these are the length scales that I'll be talking about today. And of course, one can move even more and go to something called megaparsecs. And these are the length scales where it's not just galaxies, it's millions of galaxies together. And this is where we start to see how universe is actually structured, right? So this is where I'll start my talk with. So as a cosmologist, what do we study? The very first thing is, what is it that our universe is made of, right? So we do see human beings, we see metals, we see non-metals, but as some of us know, that's a very small fraction of what the universe is really composed of. Most of the matter in the universe is not visible to eyes, or for that matter, any of the telescopes. And that's basically our dark matter and dark energy. They could be individually, each could be like a seminar. But it's interesting to understand the composition of this universe. And of course, the moment we start to look at the composition, the question are, what are these things that we are unable to see and they comprise the maximum energy of the universe? And to be honest, we don't know much. And I'll stop there because again, I can take up questions later if required. How is the matter distributed? So, okay, we have come to terms with the fact that what we see is just a 4% thing. But this 4%, how is it distributed? And that is something I'll come to later. A lot of people research on why do we just have matter, right? Because initially, when we talk about the evolution of the universe, there is equal likelihood of having matter and antimatter. So there is that. But mostly today, I'm going to focus on the last part, which is given some initial conditions, some way the universe started, how did it evolve to what we see around, right? So probably in Bangalore is not the best place, but if you go slightly outskirts, you will see a sky studded with stars. And from some Big Bang or something that I'll come to later, how did we get here? And what are the crucial periods that we want to study here? And the beauty of cosmology lies here. Unlike traditional history, where if you have to study the past, you have to look at inscriptions, you have to look at your primary sources, secondary sources, and try to interpret things. In cosmology, we can directly see the past. And that's what makes it a more interesting discipline and probably less speculatory. And the reason for that is very simple. Light takes a very finite time to travel to us. So we are looking at sun, and the light takes roughly 8 minutes from sun to reach us, which means that we are already starting to see the past, right? Sun, what we are seeing is 8-minute-olds, and you can just stretch this. You can stretch it all the way to all the length scales that we talked about, light years, thousands of light years, even mega light years. So when we see those things, we see them as millions of years back, right? So we can actually build telescopes and see the past. And this is where I'll focus on. So the evolution of the universe itself, as we understand today, comes with a very tiny perturbations. And I'll just play a video to highlight that. So what we understand is we had very tiny blips in the densities all over the place. And what you are seeing is a time lapse in units of billion years, which is the typical cosmology time scale that we talk about. And slowly what you start to see is these high density points get seeded with these stars and galaxies, and they start to emit light, right? So as we approach a few billion years, suddenly there is illumination. This is something what we call as cosmic dawn, something that I'll elaborate in much detail later. And then this continues. Of course, all these stars have very limited time. So at some point, you will start to see tiny explosions, right? So one of the very massive stars, when they die, they explode, and they enrich their environment with lots of metals, which in turn then helps to form more stars. So it's like a nice feedback process that leads to a lot of structures. And this is what we see in the night sky today, right? So this continues this kind of process, but the idea is that if you could just take a step back and look at the universe as it is, you would see that these are arranged in a very specific pattern. These are called filaments. And these are the regions where the density of the universe is slightly high, and therefore you will see the stars being there. So coming back to my presentation here, the question is, how did it all happen? So this is like a summary of all I have been talking about till today. We start with something called Big Bang, and this is basically one of the possibilities, probably the most accepted possibility, because it does explain a lot of things we see around us. Very close to the Big Bang, we had a period where universe expanded exponentially, something we call inflations. And roughly around this time, we are talking about already a few 100,000 years after the Big Bang, that we had these first light coming to us when the first atoms in the universe formed. And we can still see it. As a matter of fact, this was awarded Nobel Prize in 1965. When we first detected this relic of the Big Bang called cosmic microwave background. And our field of study starts right there. So since the 60s, this part of the universe has been studied in a lot of detail thanks to different experiments around the globe. So we kind of understand how universe was in its very infancy when it was almost 1 year old or less. And fast forward to today, as an adult universe, we can see all around us with state-of-the-art telescopes and basically see how the structures are distributed. But there is a gap here, and this gap is when the very first stars formed, right? Because we see stars today finally implies that they must have started somewhere, and this is what we call as cosmic dawn. That is something we don't understand, because in some way you need stars to form stars. So it's a chicken and egg problem leading up to the question, how did it first start? So in some way you know the universe as an infant, you know the universe as an adult, and you are asking the question of how it was as a teenager. And it's not a very linear process, right? You can't just interpret just by looking as an adult of how they were. It's exactly the same with the universe. So then you have to go out and build things that can directly see these parts of the universe. And that's precisely what we do. And just to give a rough time scaling picture, of course, what we are showing here is a very linear looking picture, but it's actually not. And one of the very nice way to interpret this is you imagine this entire thing from the Big Bang to today happened in 1 year of time. Just compress everything. And if you do that, we are basically studying January of the universe, which is where the Big Bang happened, which is where the first atoms formed, and this is where the first stars formed, right? And just to look at this perspective, we are somewhere here. The final month of this 12-month cycle. So we are really probing the very past of the universe, roughly just a few fraction of the total age of the universe. And of course, all the scientific revolutions that we are seeing is the final second. So in cosmic time scales, this is almost negligible. Okay. So the questions that we are asking is, okay, we had something right here, the first atoms have already formed in the universe, but there are no stars and galaxies, right? So it's all just hydrogen gas at this point. Universe, the most abundant element is hydrogen. At some point, you do have these stars forming. Somehow, we still don't understand that. But what they do is stars radiate. We see that in the night sky. And they begin to transform the universe, right? Because stars, of course, affect their neighborhood, which in turn affects more things. And finally, over a few 100 million years, you begin to see the entire structure of the universe transformed because of this. So the question that we are asking is, what is the nature of these stars? The very first stars in the universe, are they exactly the same as what we see today? Or is there a difference? And of course, there has to be a difference. When did they actually form? Of course, I said January, but the exact time scales are completely unknown here. And how exactly they impacted their surroundings? Of course, we have a lot of models, but very little data to basically distinguish between what is correct and what's not. And these are the key questions that we are asking with our research. And how do we see it? So as an astronomer, when you look at a period, okay, this seems exciting to me. The first question that we ask is, how do I observe this and verify this? And the source that we have chosen is nothing but our hydrogen atom itself, given that it is the most abundant element in the universe. So hydrogen atom is the simplest atom. You have a proton and you have an electron. They have something called spins. And if there is any process that can change the spin of electron, there is a specific signal which is released at a very specific frequency. And this frequency is 1420 megahertz. And I'll come back to why this is important. But the idea is, if we had to design a radio, this is in radio frequencies, if we had to design a radio and tune our radio to that frequency, we should be able to see the hydrogen around us. And that is exactly what's been done for different galaxies. So this is one of the pictures of our nearby galaxy. This is typically how it will look when, say, a Hubble telescope sees it, or one of these JWST or powerful telescopes see it. But the same picture, if you could see at these frequencies, basically you start to see the hydrogen gas, you will get something like this, right? So this brings me to the very next part, which is our universe is intrinsically multi-wavelength. Our eyes, we only see a very small part of the spectrum, which is visible spectrum. They tell very little to what's going on. And in order to understand everything, we really have to look in other wavelengths, right? So this is, I think, analogy we all understand, which is this blind man probing the elephant and deducing different things. And it nicely says our own experience is rarely the whole truth. As philosophical as it gets, this is also true for astronomy, which is if you look at a very specific wavelength and probe the universe, what you will really deduce will be one of these. And therefore, you really have to bring everything together and then lay out the whole picture. And just to give you a glimpse of how that is, let's look at our own galaxy. So if you go to a really pristine region and look at the Milky Way, you will see something like this. Very beautiful, great experience to witness this. But again, as I said, this is visible. This is something our eyes can see. But we can also go in different wavelengths. And you can see how dramatically this changes. If we could just change our wavelength to X-rays, which is one of our next talks, you will see a completely different picture. I can also tune to infrared. I could tune to our favorite hydrogen signals. And you can see how dramatically these structures are changing. And they are telling us a lot of different things, some of which will be covered in the next talk. But the idea is that you really need all of this information to understand the entire processes that are happening here. Right? All right. So this is just a summary of our Milky Way. And because we are primarily interested in this specific signal from hydrogen, we are mostly looking at the faintest part, which is megahertz frequencies. And I'm sure everyone in this room is familiar with these frequencies because of our radios operate here, right? So 100 megahertz, 98.3, 95, these numbers are all those frequencies where we can see our universe. And it's not one size fits all. So if you want to see these wavelengths, you have to build very different kinds of instruments. Again, some of it will be discussed later and some of it will be discussed just now. Actually, these instruments are right in front of you and I'll describe them a bit. Right? So focusing on what we see, we observe universe not in the visible but in radio wavelengths. And our understanding is that we want to detect this faint signal that's coming from the first stars in the universe, which we can very clearly see in radio, not so clearly in the visible light, unfortunately. So we can't really see them, but we can kind of see them by building telescopes. And this field itself is fairly recent compared to astronomy. Astronomy is millennia old. People have been stargazing since the humanity started. But this is roughly 1930s. So we have Carl Jansky here, who was designing a system for communication, because of course these frequencies are what we use for mobile phones these days, Bluetooth, FM radio and whatnot. So he was doing a similar thing and he started to see some unexplained signal, which was not aliens. So he started to see that and he started to see that it repeats. It repeats every 24 hours. And eventually it led to the conclusion that universe is sending us something which is in the radio wavelengths. And Groth Reber here got very excited about this prospect and he literally built this entire telescope in his backyard all by himself and he started observing the universe at these frequencies. So this is in some way the birth of observing this in radio, what we call as radio astronomy these days. So we do very similar thing, but of course with a lot more accuracy, which is we design these kinds of very differently looking radio telescopes and let it observe the sky signals and then try to deduce what can we say about the first stars from the data that we collect. So of course, the data that we collect is not pristine at all. Okay? So as a experimentalist, I will design a receiver, for example, FM, right? We all have FM in our phones. At 100 megahertz, I want to see the signals from the first stars, but I will probably listen to Akashvani. And that's a major contamination to what we can do with astronomy. So the very first thing that you will see in your data is terrestrial. Human beings, electronic devices, all kinds of transmitters, and Girish in the next talk will talk more about it. And units really don't matter, but do pay attention to the numbers here. So in whatever units we are measuring the power, this is roughly 20,000 or so. Suppose we could somehow get rid of this. The moment we get rid of this, we will start to see this beautiful galaxy. Just like what we saw in visible, we could also see this in radio. And it's, I would argue, more exciting. Nevertheless, it's still a contamination, because what we want to see is beyond our galaxy. What we want to see is the first stars, and therefore, this is a problem. This is yet another thing that we have to deal with, what we call as foregrounds, which in turn is very interesting to understand the processes that are happening in our Milky Way galaxy, but a nuisance for cosmology. And again, the units, it has of course reduced from 20,000, we have gone to 2,000, but still not there yet. Suppose magically I could subtract it out completely with whatever magic. I will still not go to the signal. There is something at 10 or so, which is my telescopes that are here, they are not ideal. They do have their own contaminations added. And that's exactly what you will see after you have taken care of these things. Finally, if somehow I could also get rid of these things, I will finally get down to the signal that I'm looking for and look at the units here. So we are looking at 0.02. So just to recap, we basically take this system here, put it out in one of the pristine locations, we start collecting the data, and we of course start to see the interference. We somehow fix it, we get back to our galaxy, we somehow fix it, we get to our own contaminations from our telescopes. And finally, if we are very meticulous and very accurate, we should be able to get down to the levels of the signal. And the intensity difference between this signal and the brightest of the contamination is roughly 1,000,000 times. Right? So what you see is 1,000,000 times or more stronger than the signal from the first stars and galaxies. And this is the primary challenge of our field. So people who are more technically oriented, just one slide to show what kind of signals we are looking at. And we measure these powers in Kelvin units at different frequencies. But we really don't have to get into the details of this. One thing that I also want to convey here is, given that we don't know what the first stars and galaxies looked like, as a matter of fact, that's why we are studying this. We also don't know what the signal should look like from them, right? So it's a chicken and egg problem. We want to understand something by observing something from these sources, but we quite don't know what we should be looking for, right? And that's why you see so many colors. These are all different predictions from physics of what these signals should be like, but it's possible that none of them is true. And therefore, then we have to then go back to our drawing boards and start asking more questions. So, what's exactly happening at RRI, you may ask? We are trying to build these telescopes. And these can't be off-the-shelf telescopes that we can buy off and use it, simply because, as I said, our contaminations are exceptionally high, right? 1,000,000 times or more strong. So we have to custom build these kinds of things in our own institution and then take them out and observe using these instruments to get down to the accuracies, right? We have to make very precise measurement of what the sky is like. So in an ideal world, we would be seeing something like this. You have these first stars, and we have these pristine signals from these first stars coming to our telescope. But of course, the reality is something like this. You have first stars, of course, but you also have your galaxy, you also have terrestrial interference, and you also have your own telescope. And what you really get is sum of all of these things. And then your job becomes to how to subtract each of these components to an accuracy better than 1 part in a million, which is 0.0001%, and then uncover the faint signal which is coming from these first stars. So that's exactly what we do at RRI. And the telescope that we use is called Saras. These different models are basically different stages of evolution of Saras. And these pictures highlight a few. These different shapes that you see is all because we again require measurements to be very, very accurate So we play around with a lot of designs and see how we can make our telescope be more accurate. And that's precisely the reason these days we have started floating this on lakes rather than observing more traditionally like how other people do on land. So it's not only my work. These kinds of efforts are by construction very interdisciplinary, and it does require expertise from very different domains. So we have lots of bright minds here at play. Girish right here in the audience who will talk more about a few other aspects. We have Narendra, Vishaka here and a few other people who are part of our team. We have a very nice handshake between the techniques and the science parts. So at RRI, we almost work hand in hand with different aspects, because you have to design these systems, you have to build them, you have to test it, you have to take it out to the pristine locations, do your observations of the night sky, come back, analyze the data and see what you can tell of the first stars. So this is a huge range of things which does require expertise from all different areas. And of course, in the recent past, I can't go into the details of this, but in the recent past, we have had very significant results from Celeste telescopes where we could get very important clues about the nature of the first stars and galaxies. However, this signal, even as of today, is undetected by anyone in the world. And we are roughly, say, 6 or 7 experiments worldwide who are trying to do this, pushing the limits of sensitivity every day. So it has given us nice hints of the nature of these first stars, but we are still to pin down the actual signal, and this is one of the most sought after things in the field of cosmology. So with that, I think I'll close, and I'll request Girish to take up and talk more about what kind of efforts we are doing at RRI in order to get to the required sensitivity.